So,
All right.
cut. Action. All right, so here we are in the DVTRTOS main project folder. So in here we have everything separated out into subfolders for easy to understand. So like we have documentation, and here is going to be the Doxygen, which makes an HTML. So you just go to HTML, open up the index. There's our documentation. We have app, build, core, and debug. Debug we don't really worry about. These other ones are just made by TI RTOS or SysBIOS, and we don't have to worry about them. We don't have anything that we should have to edit in those. The main ones we do is app, really app, core. Build is also, it just holds our like linker for our MSP430. So there's not really much there. So inside the app, we have, actually, let's scoot back. Let's start with how you can configure like a SysBIOS. So you have this task.config at the bottom. That's another project, don't worry about that. So double click task.config, and this is like your SysBIOS, and this is like tells you different things you can add to your project. You can have different tasks that you have. Currently we only have one task, which is the comm task, and then the user task, which is whatever our user is going to be doing. Various semaphores, you can make a logger, you can do hardware interrupts, software interrupts, set up the clock, look at memory, look at power. Those sort of things are all in here, and they're kind of like easy to use and kind of graphical, so you can kind of see how everything works and does. So that stuff is that. So I'm going to close it. So moving to our code. An application, this is where like literally application kind of layer code is going to be held. So any sort of function calls, and when we need like the CC1120 sending SPI, that's going to be in our core. But like what the actual program is going to be doing, that's always going to be in your main and in your app. So like anything, like a normal C program, we have main.c. So open this guy up. This is all the documentation we have. We include a system.h. And then we have to function prototype our tsat init. So our main's really, really simple. We're stopping the watchdog timer. We're doing tsat init. So we're initializing all the ports and stuff like that. And then do BIOS start. And BIOS start starts the SysBIOS. And once this starts, it never returns. It should never return. If it does return, which it shouldn't, we'll have this guy, which will kind of tell us that if this ever returned, an error loop to tell us, hey, something happened. tsat init is this beautiful thing. So all we're doing here was we're initializing all the ports to be sending out, being an output, and sending out an active or a 0. So they're all going to be outputs giving a 0 voltage reference. We do that so that all the ports are active and we don't have any power. It just optimizes the circuit. It optimizes our MSP430 by having all of them set as low outputs. Moving forward, here's how we do the 5-volt regulator. So if we defined external power, then P6 equals this, which means it's on. So that means external power, we're going to be using external power, so we're turning B6 on. If we're not using it, then we toggle bit 6, we turn it off, because that's the power, the regulator enable. So we're just enabling and disabling that regulator when we need it. So if we're not using external power, then all you gotta do is pound define, don't pound define that, and it works. And I'll show you how this works in a sec. So see how this is like grayed out? So this is like grayed. So whatever's grayed won't be in the program, like won't be made whenever I compile it. So this code won't even be in our C because I defined external power. So it's a way that we can like set up configurations and not have code inside our program and doing it like in compiler on the computer, not have to do like an if statement on the CPU. So after that, this is that edit that we had to do, that P2.0 when we messed up. So we had to set P2.0 as an input and make sure that's set to 0. So that's all we did here. It's pretty easy. And then we initialize the SD card. So that's the SPI stuff for the SD card. And yeah, and that's all tsat init, and then we do on the BIOS. So with the main.c, it also has a main.h. So here's where you set up all your configurations. So there's only 2 currently. So we select the way we want to transmit data back, either LIFO or FIFO. So if you define LIFO, then that means it's last in, first out. If I just uncomment this and comment this, now it's FIFO. So that's how you select between different like configurations. So here's the external power. So last time we had seen that this was grayed out because we're using external power. So if I come here and I do that out and I do internal power and we come back here, oh, I gotta build it. And I rebuild our program. Little do you know. So I rebuilt it. Now external power is grayed out, and now the other one's working. So that's kind of shows you how these work. So that's like the simple kind of startup of the sysbios, initializing the TSAT. Later on, if you have any more initializations, they can go into that function. But the main point of this is just initializing and then starting the BIOS. So that's all that the main does. So going to our COM is our only task that we actually have that we're going to run, and it's kind of big. So these are tons of pound defines that we can talk about as we go along, and function prototypes. So one thing that I made was a better wait millisecond function. So instead of waiting like NOPs or waiting like cycles, it's not really RTOS efficient. You want to put it into like a task sleep. So they actually have a function that sleeps. So all I gotta do is call task sleep and pass it a variable. So in your milliseconds. So this will let the task sleep and it'll allow other tasks to be going while something is not being utilized. Here's our create packet function. Oh, I lied. This needs to be removed. So it's a good thing we're seeing this. I'll just do it later. So create packet function needs to be removed. The comments for it. All right. Here's manual calibration. This stuff is just straight up from the reference design or reference stuff. This is just manual calibration of the CC1120, as well as this is a long one. All manual calibration. I got rid of the tick function or like a timer to set how many packets we send. We're not going to do that anymore, so I got rid of it. And then this is another one straight from the reference is calibrating the oscillator. So that's how you do that guy. So here's our communications task. So first thing we're going to want to do is we have a variable called TXRX. So that sets whether or not we're in transmit or receive mode. So I'm going to set it in receive mode at the beginning. You're going to set up interrupts for your P1, so because P1 controls all of our SPI. So set all that stuff up. Go into here. We're going to initialize the SPI for the transmit for the transceiver. We're going to send a command strobe to reset the radio, and we have to wait a few seconds or a few milliseconds. And then we're going to send it all the data to configure the registers, and that's what this does. So this sends data from transmit setting, and transmit setting is in the core. I'll show that in a sec. So this will transmit all of the data that's in the transmit setting register to our thing, and that'll set him up into 915 megahertz with a certain modulation, all that kind of stuff. Then we do that manual calibration and the calibrate ROC, and we go into our main while one loop. So in here, we have two main loops. We have the while it's in transmit, and then down here we have the while it's in receive. So there's two main things that are going to be in. In the while transmit mode, we're going to set this. These are setting the LNA and the PA of the CC1190. So we are turning the power amplifier on and turn the low noise amplifier off. Because when we're transmitting, power amplifier needs to be on, and the low noise amplifier needs to be off. So once we do that, then we just do a for loop. So currently I'm sending 10 packets. So this is what this for loop does. We're going to create a packet, wait, we're going to send that packet out with this. So we're going to write to the FIFO buffer. Then we're going to send the command to send that packet. We're going to wait for that interrupt to come. When the interrupt comes, we're waiting half a second. We're we're reading whatever error we got. If we got an error, we're going to reset the transmitter. If we don't, then we'll just loop back up. So this is every half second. So we're going to send 10 packets. So that's roughly about 5 seconds. So if we wanted to send for a minute, this would be 120. But right now for testing, I just have it set to 10. So that's what it's going to do. It's going to create a packet. It's going to wait. It's going to get an error message. If there's any errors in here, it'll tell us. And we'll refresh the transmitter. We'll send the reset. Yeah. So we'll send that. So that's just kind of the loop that it does, right? So then once it's done sending these 10 packets, it'll set us to a TX RX. It'll go back into receive mode. So now that we're in receive mode, we set the LNA on and turn the power amplifier off. And now we're going to sit and we're going to send our receive mode command, and then we're going to depend on an interrupt. So it'll send us another interrupt whenever we receive a packet. So once we receive that packet, we'll wait, and we'll pull that packet out of the register. We'll check that for errors. Check it again for errors of the bytes. And now, once all this error checking is done, we're going to command parse. So we're going to look at that R bytes, and we're going to find out if any of our useful data is in there. If it is, it'll set up accordingly, and I'll show you how the command parse works. After that, we will transmit. Yeah, and we'll set it back to receive mode, and it'll go back up, and it'll wait. But so with that command parse, we can open that guy. So here's what we're doing. So we're getting a command, which is 127 characters. I set it for 150 for good measure. I can change that probably. But so all you're doing is a string compare. So if the command is equal to any of these, so tsat awaken voltage, tsat awaken log data, credits, buzzer on, buzzer off, LED off, do something, right? So right now, if it says voltage, then it's going to set up our LNA and PA for transmit. It's going to set it to transmit. And then packet select allows us to select which packet we're going to be making when we go back into our transmit. So packet select right now is voltage, or it can be log data, or it can be credits. So these are the only 3 that actually return packets. These other ones just turn on and off certain features and whatnot. Yeah, so going back to packet select, that's not what I wanted. Yeah, going back to packet select, we can see that in our COM task here. So when we create a packet, we're going to give it a buffer to fill, and we're giving it packet select so that it knows like what we want in that buffer, and then it's going to send it out. And that is pretty much all how transmit works. How transmit and receive work. Here's that COM interrupt. So when we were just waiting for that pin to go low, we're going to post a semaphore, and we're going to clear the interrupt and get out of there. Pretty simple. This is that command parse we just looked at. So that's how our COM task is going to work. One thing, so now we can look at that packets, how packets are created. So whenever we create a packet, we're given a buffer to fill, we're given a pack select. So here's where we say if pack select equals voltage. So if it's voltage, we're going to fill that buffer like this guy, tsat awakened. We're going to run power test, which returns a buffer that has the voltage values in it in character format. So we can pull the 0, the 1s, and the 2 spot, and that'll return that value. And then that fills here, and this guy just fills up any empty ones. See how this is 21, and here's from a 22nd all the way to the top of our packet lin, which is 100. So we're sending 100 byte packets. It'll fill it up with just like null with like an empty. And so here's log data, tsat awaken log. So tsat logged, and all we're going to do is call this function called pull log data. So it's going to pull either the first one, it's going to pull 1 byte at a time, and it's going to increment down the count for the address of the log. So pull log data, you're going to get whatever bytes you wanted, and then it's going to decrement the address. So now you have an extra space to put something, and then that's going to work FIFO or LIFO, whatever you define. That's how it's going to pull. So we're going to pull 4 bytes. So we're going to pull 1, 2, then a space 1, 2. And then again, we're going to fill the rest. And this can be changed. You know, we can pull 30 bytes or whatever we want, fill it up all the way to 50 or something. But that's just how I'm showing it now. And then if pack select equals credits, I kind of use the string function to do this. So transmit buffer, I'm going to fill it with this string, tsat awaken created by. So you just fill it with that string, and then I'm going to fill the rest of the buffer with that. This one's kind of easy to use. And so that's how you make your packets. Packets.h, I don't think. It just holds your includes. And then, oh yeah, the create packet function prototype. System.h is your big A include file. This is all your includes that you'll need. So kind of like the NISI board, we have NISI.h. You include system.h and everything, and it'll include everything, all the functions that you might need. So lastly is the user's task. So this is what the user will use to make his or her own task. It should run just like your normal main would in any other program. And so that's kind of how I wanted it. So currently the user main, all it's doing is it's going to log two things. It's going to log 72, the value 72, and the character V, and then 73, the character V, wait 2 seconds, and then do it again. So this is just a simple loop to prove and to show how the log function works and how FIFA LIFO works. So I guess, so as that kind of concludes our application layer, our application .c's and .h's. Do you have any questions on how it worked? Did you catch all of it? And I probably explained it fast, but.
I think the one thing that's missing is, this might be for beta, is the complete TSAT system code.
What do you mean?
Like, because in our final demonstration, Dr. Morgan, might have the antenna pointed at the TSAT and then move it to signify like its loss. So does it know that like, hey, when I don't receive this confirmation packet, I go into sleep or I go into receive mode? Or
Yeah, so it's sending for 10 packets and then it's going into that low power receive mode.
Okay.
So that's what, and so it just, so its default state is in that low power receive mode.
That's where the Earth Station will have to ping it.
So the Earth Station, yeah, and it has to receive a good packet before it'll start transmitting.
Before it transmits another 10.
Another 10, or really 120 is what it should be, but yeah.
So 2 minutes. So
Mhm.
receives a ping, transmits 2 minutes.
Transmit them, yeah, whatever. It can be defined, whatever, yeah.
Okay. I think that was just the one.
Yeah, so that's kind of how, yeah, so the comm task is just going to pretty much honestly sit in this receive mode.
And then,
Yeah, in this receive mode, waiting on this pinned, waiting on that interrupt until it receives a packet. And then while this is pending, the user, this is when the user is going to be doing all this stuff that he wants to do.
yeah. Makes sense.
Yeah, and then, yeah. So that is all of the application layer stuff. So kind of definitely down. I think next I want to talk about the logger, but I'll kind of close this out for now. Oh yeah, we also have power driver test and power test. Those are just to test different functions. So now we'll go to the core. So this is split into two folders. Your comm config. So this is the CC1120 EasyLink. This is your config file. So this is what holds your register values. So your carrier frequency, I need to change what these are, but this is the transmit settings. So this is all that the registers that need to be configured and the values they need to be. And you can copy and paste those from this if you need to, if you want to change it. But yeah, so that's just like copied and pasted, put there. So this is what we need to send out. So that's if you want to change something, it's in that comm config in your core. Your comm SPI, this is all the SPI code that needs to be there for you to run SPI for your CC1120. These are kind of from the reference information. I only changed probably like the pins and the ports that they're using. So it's, I mean, I probably won't go into depth about it. Power monitoring, so this is how we're doing power monitoring, just with the A to D. So we're setting up the A to D. We're doing a loop of 10 right now, and then we're just averaging those 10. So doing 10 samples, averaging that, and then sending that over through whenever that's that power test. We're filling this buffer up with that value. This is using floating, so that's gonna have to change. We don't want to use floating in our power test. So that's something that'll be changed in beta. Is not, you see right here, this math right there is floating because conversion is a float. So I don't want to do that. So, but I can do that fairly easy. I'll just have to look at pressure release slides and convert that and not do a float, and hopefully find an easier way to pass these instead of using this ASCII table thing. But I can figure that out. So that's power monitoring. SD card. So the drive. This is the SD card driver that includes all the low-level I/O stuff, but we don't really care about. The things we do care about is how this logger works. So logger.c. So initialize SD card, pretty standard, just like setting up. We're setting it MMC init, and it returns a status byte. And if this is if it is anything but a 1, it'll just keep, or not a 0, it'll just keep doing this. Once it hits 0, then it'll jump out of the while loop. That means we did it right. It's set up correctly. Then we'll read the card size, which we'll set to the max address. Then we'll write a sector. Oh yeah, I'm gonna delete this actually. This was just to clear that sector because I was having a null, so I don't need that. So we're gonna find the max and then return 1. So log data doesn't matter if we're doing LIFO or FIFO, it always is the same. We do a few checks at the beginning, so if we're in transmit mode, we're going to return and we're not going to log anything, because if we're in transmit, I don't want this to be doing SPI. If the current address is 0, which is the null character, then we're going to want to increment it just to 1. If the max address equals current address, that means our SD card is full. Then we're going to return FF. So that's an error message. So right now I'm having it not rewrite old data. I'm having it just, if the SD card's full, it just stops. It won't log anymore until we pull that data out. But of course, that whatever the customer wants. But that can be configured. So all this does, so an SD card is separated out into sectors, which are 512 bytes. Okay, so it's 512 bytes, 512, 512, 1 sector, 2 sector, 3 sector, all the way up to like your current address divided by 512, so however many sectors that is. So how I did my math was, so our current address right now is 1, right? So 1 divided by 512, and these are integers, is going to be 0. So that's right. So in sector 0, that holds our first address. So does that make sense? So like 0, we're going to read that sector as 0. And we're going to save it into a temporary buffer. And now, temporary buffer, the first one, we're going to set it to that first value, increment the current address, set the next one to name, increment it, and then we're going to write that sector again with the changes we made to the temporary buffer, and then go idle and return 1. So that'll fill the first 2 bytes. When we return, it'll increment it again, fill the next 2, fill the next 2, fill the next 2. And so this is like starting at 0 and filling it up this way, and that's one way. We're not changing the way that works. If we pull log data, so here's again like the FIFO or LIFO, whichever one's defined. So since LIFO is defined, it's not colored. FIFO is not going to be included. So if we were doing first in, first out, then we do a check if our FIFO address is equal to our current address. So say we were like 32 was our current address, but we read all the way up to 32, so there should be no new data. Then we're just going to set both of them to 0 because we've read all the information we needed, because 32 is just sitting there. So we're setting them both back to 0, and then we're going to go idle and return that error of 0xFF. If it's not like that, if it's 31, 32, or whatever it is, we're going to read the sector, increment that address, go idle, and then return whatever value was in that FIFO address divided by 512. So that'll give us whatever value was in that spot. Oh yeah, and the modulus of it. So that's like, yeah, so the remainder. So LIFO is probably the easiest one. If we decremented it, if the current address is 0, we return it. That means there's no data. All we're going to do is to read that sector. We're going to decrement the address, go idle, and then send whatever we just received back with that same thing. The higher the address, the more data we have. And in LIFO, yeah. And so something to address in like FIFO, I need to make this more circular. So when we're doing FIFO, it needs to be more of a circular buffer so that it can loop back on itself when it's empty. but I can deal with that later. And we'll talk to Professor Willie about that. But so those are how those two kind of work. Yeah. And so that's the driver's with the SD card. And that's how the SD card works. And that's pretty much how everything works.